All right, so we're gonna talk about, sorry. Today we get to talk about the derivative and differentiability, which is a really exciting day for all you lucky ducks. Um, we've talked about a lot of things so far that are um, sort of scaffolding leading us into this point. The whole reason we reviewed the things that we reviewed was so that we could talk about the derivative. Now, some of you I know have had some sort of calc before. Maybe you had it in high school, maybe you took AP Calc or Honors Calc, or maybe you even talked about this a little bit in pre-calc. If you did, you probably learned that there are a bunch of rules for taking derivatives. Those we're going to cover in Chapter 3. In Chapter 2, we're going to mostly just focus on what the derivative is and how to compute it using limits, and talk about how we know if a function has a derivative or not, and just sort of look at some graphs and be able to make connections between the derivative and a graph. So we have a lot to do here in 2.6 to end this chapter. And then we'll talk about derivative rules. There are so many of them in Chapter 3. But right now, let's just focus on looking at the derivative. Okay, so we have we're going to find derivatives of functions, use the limit definition. We're going to use derivatives to find slopes of tangent lines and equations of tangent lines. We're going to apply derivatives to application problems, including position, velocity, and acceleration. We're going to relate differentiability and continuity. It's loaded. There's so much to do today. Full disclosure, I have a 4-year-old who's homesick from school, so we're gonna try to do this right now. The tangent line problem. Nonlinear functions have varying rates of change. So far, you've only talked about slope as it relates to straight lines. So linear functions have a constant slope throughout. However, this function, this curved function that you're seeing here, is not linear. It's not a straight line. Therefore, at any given point where we look at this function, we can see that the slope of the line that's tangent to the graph would be different. If you've never talked about what it means to be tangent to a curve, it basically just means that we're creating a line that sort of butts up to this curve and just follows the direction at a specific point. It's a line that runs like right next to the curve. It hits the curve in only one spot. So when we're tangent to a curve, it just means that we hit the curve in one spot and that's it. It's just a straight line. So how can we describe and find instantaneous rates of change which are graphically represented by slopes of tangent lines at different points on a function? So that's the whole idea here, is like, well, how would I be able to talk about the rate of change or the change in y over the change in x if the rate of change is different as I move throughout this curve? And that's what we're going to be talking about here with the derivative, is how we can examine the slopes at any point on the curve that we want. So we start with the idea of using slope of a secant line as an approximation for the slope of the tangent line we're interested in. So the secant line is just going to be a line that goes through 2 points on a curve. So consider this example here. So the secant line here is this green dashed line. You can see it says secant line in green. I know it doesn't look that green on the video, but the secant line is the dashed line. Now, right now we're focusing on this curve f of x. The curve is this black curve that's labeled. The points P and Q are on the curve. So the secant line goes through points P and Q. Now, notice that the secant line can't really approximate this curve very well. I wouldn't say like, oh, this curve is kind of like this secant line. I mean, I guess they kind of are heading the same direction. They're both heading up as you move from left to right. But the secant line is really just gathering these 2 points and connecting them on the curve. That's all it's doing. But what we can do, though, is talk about the slope of the secant line and then consider what happens as we maybe move these points P and Q to be a little bit closer together. Now, your page, I believe, has an X here. What we want to do is we want to mark this coordinate a little bit differently. So the X that you have for this left coordinate can stay, and that's going to correspond to this point P. And then what we're going to do is we're going to just add some quantity to it, and we're going to consider the difference between this X value and the next one to be the quantity H. So if we're starting at X, well, if I move over H units, then I can call this next X coordinate X plus H. So these have a distance between them of about h units. We have to think about this in generalities. And this corresponds here to the point Q. So this would be the x coordinate. Now remember that we also have these corresponding y values for any x coordinate on our graph. I'm going to try to make this as straight as I can. But the y coordinate here would just be the function value at x plus h. And then over here, our y value would just be the function value at x. So in that case, we could label these coordinates. Q, well, we could first label the first coordinate as x, f of x. That would be our point P. And then our point Q would be x plus h, and then the function value f of x plus h. So now we have everything labeled on our graph. So the question is, well, what's the slope of the secant line? You'll see that we have some information down here that pulls all this back together. Maybe I should zoom out a little bit because I feel like it maybe would be helpful as soon as I do this. I'm going to have a hard time zooming it back in exactly the way I want it. That's all right. Okay. So the idea here is that we can come up with the slope of the secant line by taking the change in y over the change in x. So maybe I'll write this over here in our blank space since we have this. So we can say that the slope of the secant line, and usually we talk about slope, remember, as that variable m, is the change in y over the change in x. So this is going to be f of x plus h minus f of x. That's the difference in the y values, just looking at these y coordinates. And then for the x coordinates, we'll take x plus h minus x. And when I simplify these, I end up getting f of x plus h minus f of x divided by h. Now, if this looks familiar to you, should, because it's pretty much exactly what you did with the difference quotient in the last couple of sections. When we talked about the difference quotient in the last few sections, we were focusing on a specific value of a. So we talked about f of a plus h minus f of a divided by h. Well, if we're going to talk about the derivative, we want to expand this out to all the different possibilities for the values that a could take on. So we're going to just consider this to be a general x. So this is going to represent the slope of the secant line. We can now just go ahead and look at this. Logic tells us to try and move the point Q closer to the point P. And this is the point of tangency. So we can basically take our secant line, which goes through these 2 points. And if we move these points closer together, so you'll see in the illustration on the right, this coordinate here that used to be called Q is going to move down on the graph. And as Q moves down on the curve, the secant line is going to actually start to lower itself down a little bit. You can see it's going to sort of go like, oh, okay, well, Q is moving down, and it's going to sort of swing its way through. And eventually, as this point keeps moving down, and you can see it in this illustration, it started out up here as Q. This was your original Q. Go ahead and label that if it helps. When we move Q down, we'll just have a different point, but the secant line starts to head down. And as these 2 points P and the next point get closer and closer and closer together, what you end up creating is a tangent line. Because as Q gets infinitesimally close to P, you've now minimized this distance between x and x plus h. And eventually, x plus h is going to move all the way down to x. And we're just stating now that the difference between these two is going to be nothing. So I'm going to give you a formula for how to compute this derivative on the next page. But the main takeaway from this is that the difference quotient will give you an average rate of change. The difference quotient is the average rate of change. So it's basically just going to give you the slope of this secant line. So anytime we're talking about average rate of change, and we're going to give a couple of examples of this in a little bit, you're basically just trying to find the slope of a secant line that goes through a curve. And then when you're talking about the tangent line, you're talking about an instantaneous rate of change. So for slope of the tangent line, we're going to say that this is an instantaneous rate of change. And the instantaneous rate of change is how we would discuss the derivative. So at that moment, how quickly is the value of the function changing? Is the instantaneous rate of change. It's not going to look at 2 points, it's going to look at 1 point. So very, very cool stuff. This over here. Okay, I'm going to zoom back in a little bit so that we can do some work with these things. See if I can zoom. I don't know why it freaks me out. Okay. Excellent. Wonderful. All right, so sort of a continuation of what you were seeing on that previous page. This point started out up here. It was Q. It moves down and down and down. And as the distance between x and x plus h gets smaller and smaller and smaller, which means h is heading to 0, because I'm looking at x and then x plus 0 eventually to get me to the same value, you will see that eventually you end up getting this line to be the slope of the tangent line. Now, the eventually part is where the limit comes in. And we spent so much time talking about limits in 2.4, and we talked about one-sided limits and continuity in 2.5. That sets us up to talk about the derivative in 2.6. So the slope of the secant line is the average rate of change, which is the difference quotient. I don't know why that term always eludes me. But the slope of the tangent line is your instantaneous rate of change. And that, my friends, is your derivative. So we're now going to talk a little bit about the derivative, which is the slope of the tangent line to a curve at any given point. All right, in order to talk about this, we're going to formally define this as f prime of x. I'm going to write you a little note here so that you understand what this notation means. But f prime of x is how we denote a derivative. So this is the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Now, f prime of x is the notation. We read this f prime of x. It's like a little apostrophe between the f and the left parenthesis. If you've taken calc before, or you might come across the notation, sometimes delta x is used instead of h. So you might see that if you end up coming across some other calculus videos or worksheets or some sort of learning aids. It's just that h represents the change in the x coordinate. All right. So let's do some examples here where we compute the derivative, and then we'll look at it on the graph and make sure that it makes sense to us. I think the most important takeaway here is that we need to make sure we understand that the derivative is a slope. So I keep saying this, the slope of the tangent line, the derivative is a slope. So don't think about it as some like, oh, this is some weird abstract mathematical concept. Not really. It's just measuring the slope at a given point. So we're going to use the limit of the difference quotient to find the derivative, and then we're going to look at some graphs and make sure that it makes sense to us graphically. And I'll show you how to check in on your calculators also. So let's go through some examples. I know you have a hole punch here, but we're going to go through first example 1. Let f of x be negative 16 x squared plus 128x. What we're going to do first is find the derivative f prime of x. So find the derivative f prime of x. Now, in order to do that, I'm going to need to take the limit as h approaches 0 of f of x plus h minus f of x divided by h. So I need a couple different things here. The main thing I need to focus on finding first is f of x plus h, because I already have f of x, and dividing by h is not that big of a deal. So first find f of x plus h. I'm going to take my function, and everywhere I see x, I'm going to swap it out for x plus h. I'm going to substitute. So we'll have negative 16 and then x plus h. Now remember, I'm going to be squaring that quantity. When I square a binomial, I want to multiply it by itself. So I'm not even going to write that square notation. I'm just going to show it being squared. Then plus 128 times x plus h. And then we'll simplify this a little bit. So I'm going to have negative 16, and I'm going to go ahead and FOIL this out. We have x squared plus, now when I take the outside and the inside terms, remember you're going to get xh plus hx. Multiplication is commutative. So I'm just going to say I have 2 times, and I'm going to pick an order. I normally go in alphabetical order, and I don't want to mess that up. It does not matter if you call it xh or hx. But because I'm a little bit pedantic, I'm going to call it hx, and I don't know why I put a parenthesis there, because now I've just totally, I'm going rogue now. Okay, 2hx, and then plus h squared. Those would be the last ones. And then plus 128x plus 128h. Now I'll simplify that, and then we'll put it all together in the difference quotient and find the limit. So I'm still working on f of x plus h. So I'm going to just continue that on the next line. I have negative 16x squared minus 32hx minus 16, just distributing this negative 16 into the parentheses, h squared, plus 128x plus 128h. So that is f of x plus h. Now check to make sure that there's nothing that you can cancel out here, but there is not. So this is as simplified as it's going to get. What we need to do now is get this difference quotient put together. So now I'm going to look for f of x plus h minus f of x divided by h. So I'm going to take the function that we just found. I'm going to rewrite it. I know it's a lot to write, but such is life. Why am I not using a pencil is the question that we all should be asking. So we have 128x plus 128h. Actually, I don't use a pencil on this because it doesn't show up very well in the sunlight. All right, so this is f of x plus h. Now I need to subtract off f of x. If you want to do this in 1 step or 2, that's up to you. I'm going to just do mine in 2 because I'm the one modeling this for you, and I want to make sure it looks good. So we have minus, and then I'm going to subtract off this quantity. I'm taking off, and I'm putting it in parentheses because I'm subtracting negative 16x squared plus 128x. So that whole quantity is getting subtracted. I just marked my paper here. Okay. And then I'm going to divide this whole thing by h. You know, I'm really glad that I got this new whiteout pen because it's like a travesty what's happening here on these notes. Okay. Wonderful. Now let's simplify. So this is going to be equal to, and I'm going to go ahead and combine like terms here. I'm going to have negative 16x squared minus negative 16x squared. Remember, if you've done this correctly, these 2 terms are going to be additive inverses, and they're going to cancel out. If you need to see the step, I will show you the step because I'm the teacher. negative 16x squared minus 32hx minus 16h squared plus 128x plus 128h plus 16x squared minus 128x divided by h. All right, so here's where the magic happens. Negative 16x squared, positive 16x squared, those are going to cancel. Negative 128x and positive 128x. Now what we end up with here is, notice that you're going to want to cancel this h out of the denominator. You can't cancel it unless you can factor it out of the numerator. So when I rewrite the numerator without these 4 terms in it, I'm going to just go ahead and factor out the h. So that leaves us with negative 32x minus 16h to the first plus 128. And now I can rewrite this where the numerator is factored. And as long as I can factor out the h, I can cancel it. And now I can rewrite my expression as negative 32x minus 16h plus 128. And if you're wondering, like, wow, we're really getting to the bottom of this. Yes, we are. We just have one more thing to do with this before we do part B, which is the meat and potatoes of all this. What we're going to do is go back to this definition for the derivative. This is what we're supposed to be trying to find. I gave you a function. We just focused on finding the difference quotient. Now we need to take the limit as h approaches 0. So the limit is h approaches 0 of negative 32x minus 16h plus 128. Now, I want you to be very careful here, because so far when we've been taking limits, we've been using direct substitution to evaluate them, and we've only been dealing mostly with the variable x. Right now, we're sending h to 0. The first term doesn't have an h in it. It has an x. It doesn't mean that you evaluate this term at 0. You don't. This is going to stay x. If it doesn't have an h in it, you don't evaluate it. You treat the x just like it's part of the number. So I'm going to keep the negative 32x just the way it is. But for the negative 16h, this is where I'm going to substitute h being 0. And that means I'm taking negative 16 times 0 and then plus 128. So just using direct substitution to evaluate this limit gives us a derivative f prime of x as negative 32x plus 128. That's your f prime. Now, in section 3.1, we're going to talk about ways that are way faster to find this derivative. So if you're freaking out right now, yes, you technically have to know how to do this for your chapter 2 exam, but we will eventually come to ways of finding derivatives that are a little bit faster for a function like this. Part B is something we're going to do quickly down here at the bottom because it's short. Find the slope of the tangent line at x equals 0. So find the slope of the tangent line at x equals 0. Well, remember that a derivative is a slope, and you just found the derivative, but you found a general formula for the slope at a given value of x. This is a really powerful tool. It means that we can look at this function at any particular value of x that we'd like, evaluate its derivative at that value, and it'll tell us the slope of the tangent line at that point. So what I can do now is I can take my derivative, and if I'm just trying to find the slope of the tangent line at x equals 0, I can evaluate f prime of 0. And this is just negative 32 times 0 plus 128, which is equal to 128. Now, having a slope of 128 is almost difficult to quantify, but remember what you're talking about with the slope is the rise over the run. So that basically means you're taking a rise of 128 and a run of 1. Sorry, I don't want to do this the opposite direction. But your graph is going to go up 128 and then 1 to the right. So this is a very, very, very steep graph at that point, just because you know that that's a super, super steep slope. We're going to look at this in our graphing calculators in a couple of minutes, but I want to add on part C to this first so that we can check this in our graphing calculators. This one itself is a little bit harder to check, but we can definitely do it. I'm going to hang on to this and keep it close by so that we can use it in a minute. Okay, so for part C, we are going to do a very classic calculus problem. Find an equation of the tangent line at x equals 0. Okay, so I'm going to remind you of what we have so far. You have f of x, since this is on the other sheet, f of x equals negative 16x squared plus 128x. And then we had f prime of x was the derivative that we found was negative 32x plus 128. Now, we also found that f prime of 0 was 128. A derivative is a slope. The slope we usually call m. Now, I asked you to find the equation of the tangent line at x equals 0. If you're trying to find an equation of a line, what you need is a slope and a point. Now, you have a slope. You have the slope of the line. You don't quite have a point. You have an x value. But what we can do, though, is to find the y value, you can evaluate the original function at your given value of x. So we have the x coordinate, which is x equals 0, and we have the slope. Now, what we need is a y coordinate. So the y coordinate, you're always going to find by evaluating your original function at 0. Okay, so we're trying to find the equation of the tangent line at the point where x equals 0. Well, in order to figure out the y value, you're going to find the function value at 0. So I'm going to take f and I'm going to evaluate it at 0. And I'm going to get negative 16 times 0 squared plus 128 times 0. And I'm going to get 0. So now I have a point on the curve, which is the point being 0, 0. And I have a slope of 128. So these are the two pieces of information that I need to find the equation of a line. I always need a point and a slope. Now, the way that I'm going to be doing this is I'm going to use point slope form. This is something you should have learned way back when in algebra. It's really important. If you don't want to memorize it, fine. I think we talked about this in a previous lesson, but you're going to take y minus y sub 1 equals m times x minus x sub 1. This is point slope form. I would highly recommend that this just be something that you memorize and have at your disposal whenever you need it. This is just saying that if you have a given point, x sub 1, y sub 1, and a slope, you can plug these values into the equation to give you the general equation of the line that has those characteristics. So remember that your point is x sub 1, y sub 1, and we have the slope already. Now, of course, if you don't remember this, it can be hard to remember. Divide both sides by x minus x sub 1, and you just get the equation for the slope. So m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's where this comes from. All right, so I'm going to plug everything in. The general y stays. The y sub 1 is going to be our y coordinate. And then we have the slope being 128, and then x minus our x coordinate, which was 0. That means our equation, when we simplify it, is just y equals 128x. This is the answer to part C. I have a very important note here, and I'm going to write it down because it seems like when students first learn derivatives, they always just are like, oh my gosh, I just learned this crazy thing, and it's so wild. It's a slope. A derivative is a slope. Okay, let's not make it super complicated. It's just a slope. So what we're going to do now is we're going to graph the curve, and we're going to graph the equation of the line that we just came up with. And we're going to make sure that it makes sense. Now, we're going to check 2 of these because I'm going to give you another example after this. The second one that we're going to go through is going to be a little bit easier to see on the graph, but sometimes these polynomials are a little bit hard to see. So I don't mind that we're going over it just so that you can sort of get a sense for what you're going to be looking for. So we're going to end up putting in the original function. The original function, remember, was, I put it up here again, negative 16x squared plus 128x. So negative 16x squared plus 128x. If you want to get a sense for what that looks like, I'm going to go to Zoom 6 just so that you can look at the graph. Okay. So it's kind of hard to see what's even happening here. And that's just because you've got this really large number of 128 on your parabola. You might want to zoom out a little bit just so that you can sort of see the graph. You might even want to take your window and kind of play around with it. I find that students always get stuck here because they're like, well, how do I know what to change my window to? What we really need is some more clearance on the y-axis because we know this function's really tall. Maybe try going up to 100 and then see what happens. But you could also just plug in a couple of values to maybe get a sense for where you need to be on the graph. But I'm going to just change my y max for a minute, and then we'll see if the picture comes out better for us. It's closer, but it's not high enough. So maybe even switch your window so that your y max is something like, I don't know, 150. See what that does. I should have stuck with 200. Window, y max. Let's see. I'm even going to 225. Let's do 225. Okay, not high enough, but you can get a sense for what's happening here. Let's see. Maybe we'll try 250. We're close. Oh, so close. What about if we change our y max to 275? See how I'm just playing around with this? That's why when students are like, well, how would I know to do this to my window? I don't know. Just popping in numbers until I can see a full graph. All right, so there's your parabola. Now, you might want to get rid of some of this blank space over here. Since we already know that there's an intersection point at 0, 0, I don't know. I might start at x equals like -1, maybe just not all the way to 0, but maybe -1. The reason being, we're focusing on what's happening at 0, 0. So here's your parabola. You were asked to find an equation of the tangent line at x equals 0. And the equation that we found was 128x. Now, what we need here is we need to be able to see that at the given point, which at x equals 0, we found that y equals 0, which makes sense. It's a point on the graph. You can also see it in your table. When x is 0, y is 0. Now that we have the graph, you're going to want to graph your tangent line and make sure that it looks like it's tangent to that point. Now, I kind of feel like maybe we should have given ourselves a little bit more space down here to see the tangent line. So maybe I'll make my y minimum value something like -100. And I might move this x max over a little bit. I don't know, 2. Let's see. Yeah. I mean, I feel like this should be good enough for us to just be able to see the tangent line. So the next thing we're going to do, now that we have the graph, we see it really nice and clearly in our window. We fixed it so it looks good. I mean, remember what this looked like when we first graphed it. We couldn't even tell what was going on. But it's a parabola. We're expecting that. You talked about this in college algebra. It's a second-degree polynomial. That's what you were expecting. The coefficient on the x squared term is negative, so you know that the graph is opening down. Let's go ahead and graph the equation of the tangent line now. We're going to graph both of them together. So this is where your 128x comes in. There it is. Let's graph it. And you can see now that this graph is tangent to the curve. If you wanted, you could always adjust your window a little bit more, but what you're looking is for it to be kind of running alongside the curve. It's going to hit at exactly 1 point. Now you can start to see here how the tangent line, because it's straight, will eventually veer away from the curve. So if you were to change your window so that your y min was even smaller, like -200, you would be able to see this. There's like a delay on my video. You'd be able to see the tangent line even more clearly. So you can see how it comes out and it hits at exactly that point at 0, 0, and then it keeps going. So you can see the curve starts to pull away from the tangent line up here and then down here again. So that's pretty cool, right? We can find the slope at any given point. So like I could even ask you to find the equation of the tangent line, I don't know, at like 7. And then you'd be like, oh, okay, 7 is like over here. And you'd be expecting that tangent line to be heading this way, which means the slope would be negative. So there's so much stuff that we're going to do with this. I feel like there's so much I want to say about this example, but I don't want to throw too much at you at once. Let's illustrate another example here of how to use the difference quotient to find the equation of the tangent line. Ready? All right, this time we're going to do a rational function. So this will be example 2. G of x, I'm probably going to regret this because you know what? I'm going to call it f because I know I'm going to keep calling it f. F of x equals -2 over x. So not only is this a rational function, which means that we have a ratio of a function in the numerator and the denominator, but it's negative. So let's go ahead. First, find f prime of x for part A. For f prime of x, I'm looking for the limit as h approaches 0 of the difference quotient. So I'm going to first find f of x plus h. Now, in this case, f of x plus h is not too crazy. F of x plus h is going to be -2 over x plus h. So we don't have to square it. We don't have to do anything super crazy. Now that we have that, we can go ahead and find the difference quotient. Now, you might want to pop the limit on now. It's up to you. I know that I'm going to be doing a lot of simplifying here. And because I'm going to be doing a lot of simplifying, I'm going to wait to put the limit on because I don't want to have to keep writing limit over and over and over again. So I'm going to take f of x plus h, subtract f of x, and divide by h. So remember, this is f of x plus h minus f of x all divided by h. That's your difference quotient. So let's work on this a little bit. First of all, if the minus and negative is bugging you, we're going to work on that as well. There are a couple things you could do for simplifying this. I'm going to go ahead and get the common denominator in the numerator so that I can add these two fractions together, and then I can invert and multiply with the h. So the LCD in the numerator would be x times x plus h. So I'm going to multiply through there. So it'll be -2 and then times x divided by x times x plus h. Remember, the whole idea here is that if I decided to simplify this, I'd get back to where I started. So I've just multiplied by x in the numerator and denominator. Plus twice x plus h divided by x times x plus h. And again, if I were to cancel out the x plus h's, I would get back to where I started. And then we'll divide by h. Now that we have a common denominator, we can add these two fractions. So this is -2x plus 2x plus 2h. I went ahead and added the two fractions together by adding their numerators. So this is -2x plus, and then distributed the 2 into the parentheses. And then instead of dividing by h, I'm going to multiply by 1 over h. So when we're dividing two fractions, we invert and multiply. Now, a lot just happened. I'm going to at least get rid of these two additive inverses. -2x plus 2x, those are gone. We can technically cancel those h's out now, but I'm going to rewrite it first so it's really clear, because I want to make sure that we're only doing things that we are allowed to do in mathematics. So this is h times x plus h. Now that we have a factor of h in the numerator and the denominator, we cancel it out. And that leaves us with 2 over x times x plus h. And that is our difference quotient. Now, to find the derivative, I need to find the limit as h approaches 0 of the difference quotient. Now remember, when you're evaluating this limit, you're not messing with the x. The only quantity that's heading to 0 is the h. So when you evaluate this using direct substitution, you're just going to let h go to 0, and that leaves you with 2 over x times x plus 0. Well, x plus 0 is just x. So you get 2 over x squared. This is the derivative f prime of x, which gives you a formula for finding the slope of the tangent line on the graph at any given point x that you feed into it. What we're going to look at is the slope of the tangent line at x equals 1. So let's see, f prime of 1. Oh, I'm going to write this as a question first. Find the slope of the tangent line at x equals 1. Find the slope of the tangent line at x equals 1. Okay. Oh, look at this. Is what I've been saying this whole time. The slope and the derivative are the same thing. No one believes me. They're like, why don't you just call it slope then? I mean, we have to differentiate here when we're talking about curves. All right, so I'm looking at f prime of 1 now. So I'm trying to find the slope at 1. I'll evaluate the derivative at 1. So this will be 2 divided by 1 squared, which is 2. This is your slope of the tangent line when x equals 1. And then, of course, we're going to add on a question asking for the equation of the tangent line at x equals 1. Find an equation for the tangent line at x equals 1. Awesome. Remember that in order to write the equation for a line, I need two things. I need a slope and a point. I have a slope and I have half of a point. I just have the x coordinate. I need to find the y coordinate. Remember, though, that I'm not trying to find the y coordinate for f prime. I'm trying to find the y coordinate of my original curve, which was my curve f of x equals -2 over x. So that means that in order to find the y coordinate, I need to find f of 1, not f prime of 1. You already found that. That was the slope. The corresponding y value to your function is f of 1. The point on the graph on the y-axis when x equals 1. F of 1 is -2 over 1. Remember, our original function was -2 over x. So I'm just using that to evaluate f of 1. And then we get -2. So our point now we can say is 1, -2, and the slope we found earlier to be 2. So we're going to use these two pieces of information together, the point and the slope, with point-slope form to get the equation of the line. Y minus y sub 1 equals m times x minus x sub 1. So we're just taking y minus and then the y coordinate. That's a double negative, so be careful. Make sure you got both of them. Equals the slope, which is +2, times x minus the x coordinate. And then the last thing you need to do is simplify this. Don't leave it. I'm always going to request on your exams that you write your equations in slope-intercept form. I'm going to go through and put this in slope-intercept form so you can see what I mean. Y plus 2 equals, and then I'm going to distribute on the left-hand side to get, or on the right-hand side to get 2x minus 2. And then I'm going to solve for y. To do that, I'm going to subtract 2 on both sides. So we'll get y equals 2x minus 4. This is slope-intercept form. Slope-intercept form. You learned about it in algebra. The idea is it gives you the slope right here. That's your slope. The y-intercept is given to you by this value, y equals mx plus b. That's slope-intercept form. That's how I'm going to ask for the equations of your lines. So that basically just means solve for y and simplify the right-hand side. Let's look at this on our calculators. So we have this crazy function in here right now. It's not a crazy function, but we had to do a lot of zooming to it. This one's going to be a little bit easier to look at. We have an original function, f of x equals -2 over x. So I'm going to plug that in. Let's get the equation how we want it first. I'm going to zoom 6 to zoom standard. It's usually where I start, and then I sort of move things around from there if needed. But this is actually a really nice view in standard view because really all we're doing is focusing on what happens at x equals 1. And at x equals 1, we should have the equation of the tangent line being 2x minus 4. So let's go ahead and also graph 2x minus 4. 2x minus 4, and we'll be able to see this really nicely in our current zoom graph. I get so excited when it all ends up being exactly the way it's supposed to be. This is what it's supposed to look like. Here's your curve. The point is, what did we say the point was? Oh, 1, -2. Yes, and you can check that, by the way, in your table. When x equals 1, y equals -2. Oh, interesting. I have a little bit more to say about this. I just remembered. Okay. But we have this point on the graph, and the tangent line runs through. It hits the graph at exactly 1 point at 1, -2, and then it keeps going. So this is a really nice example to illustrate what the tangent line is supposed to look like. It just hits the curve in one spot, and then it keeps going. I believe you can check this in your calculator. Go to second trace, which is the calculate menu, and you should be able to calculate the derivative using dy dx, which is number 6. Now, it's going to start you out at your first curve, which is y sub 1. That's exactly what you want it to do, but this is just a way to check your slope. Now, you can cursor over, and it's going to show you where you are as far as x and y values, and you'll eventually see your point. So it's going to ask you for an approximate value, and you're just going to try to eyeball where it's supposed to go. So I don't know, here, there, wherever you think it is. And then you're going to hit enter. And then it's been a while since I've done this. Oh, you know what? I was supposed to enter a value of X. That's why. Sorry, do it over again. Second calculate, number 6. You just enter an X. So I'm just going to enter my value as at 1 because I'm looking at X equals 1. So I'm just going to type 1. And when I type 1, it just shows up. And now it gives me my value for the derivative as 2. And it occurs at the point 1, -2. So the point is 1, -2, and the slope is 2. I know it says 2.00002, but your calculator is just doing the best that it can to zero in on that slope for you. Okay. All right. So that's what I was going to say about the difference quotient for now. It's really important. But right now we're going to just evaluate some graphs. We're going to look at what the slope actually means in terms of applications and graphs. We need to make sure we understand what the slope represents. So here's the first example. The graph above represents the amount of money a company has spent on insurance for its employees since 1960. Estimate the slope of the tangent line at x equals 40 and interpret the answer in practical terms with appropriate labels. So really, there's not much we can do as far as actually being able to find the value of the slope here because we don't have a function value. All we have is a graph. But we can estimate the slope just using 2 points that are really close together. So if I'm going to estimate what's happening at this point, x equals 40, which we're being asked about, I can come up with a value that I think it is approximately. So maybe like going here to the y-axis and saying, okay, well, if this is 50 and that's 100, like maybe this is like 40 and like 340. I think I veered down a little bit, but that's about where that point is located. Now, I'm going to pick a point that's close. So it doesn't make sense for me to estimate a slope at a given value, maybe using a value over here, because the slope between those two would be really steep. These points are very far away from each other. So I'm going to pick something that's closer. And I might say like, well, let's look at this graph at like 30. And then maybe that point corresponds to about 300. So we'll label that point as 30, 300. And as long as I can find the slope between those 2 points, it's going to give me some sort of an estimate. Now, of course, the closer you can get to 40, the closer your estimate is going to be. So if you feel pretty confident saying, well, maybe I can do 35 and then like 310, like, okay, I mean, it's close. All we're doing here is estimating. So I'm going to get the slope here to be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I'm going to get the slope value to simplify to 4. Now, that's not enough to answer this question. We need to estimate the slope of the tangent line at 40 and interpret the answer in practical terms. Now, I also want you to check this, by the way, like, does this make sense? So you're trying to figure out, like, between 30 and 40, does that slope look like it could be rise over run 4/1? I mean, I guess it's a little bit hard to tell because we're not using like a 1-to-1 scale here. So it's going to look more shallow than 4. Maybe being able to check that is just something as simple as saying, is our slope positive? And you can clearly tell that the line is going up from left to right. So it makes sense that the slope is positive. At least you can check that. The other thing we need to do is interpret the answer in practical terms. So if the slope is 4 and we're talking about the change in y over the change in x, well, y represented dollar amounts in thousands, and then x represented years. So when we end up getting this slope value, we can say that that's about 4,000 per year. And in order to give a full answer here, we should say that, let's see, the amount of money a company has spent on insurance is increasing by 4,000 per year. So the amount spent on insurance is increasing by about $4,000 per year. Now it's increasing because it's a positive value. So if we ended up getting something where we got a negative slope, then we would say that the value is decreasing. But you can see that this graph is heading upwards, it's increasing. Apparently though, at some point it's going to start to decrease. I don't know why it would start to decrease, but for some reason the company would need to spend less money on insurance for its employees. All right, so that's how we would interpret something like this in practical terms. If you just think about this as the change in y over the change in x, and you think about the labels for the y and the x axes, I think that'll really help you to be able to put some values to that. Another thing to keep an eye out for, though, is the fact that this dollar amount is in thousands. So if you said, oh, the amount that the company is spending is changing by $4 per year, well, you might have to ask yourself, like, does that really make sense? $4 per year? I mean, maybe from one year to the next, I mean, I guess it's possible, but I mean, think about this graph over time. And it just would seem like a really small amount for it to change by year, and it couldn't correspond to something like this. So just some things to think about. Number 2, gravel is being dumped by a conveyor belt and forms a cone. If V of t represents the volume in feet cubed after t seconds, so remember that t represents time, what does V prime of 60 equal 0.37 represent? So if V of t represents a volume, anytime we change the function to be its derivative, we're talking about the change in that quantity. So V prime would be the change in the volume. The change in volume would be represented by V prime. And then the volume at this point in time, remember V of t, time is being measured in seconds. So that would mean that this would be 60 seconds. So the change in volume at 60 seconds, at t equals 60 seconds, is 0.37 feet cubed per second. All right, so there's really not much to do here other than just interpret the notation, but being able to interpret the notation is really important. So V of t represents the volume in feet cubed after t seconds. V prime represents the change in volume after a certain number of seconds. If that number of seconds is 60, the volume is changing at that point in time by this amount. So 0.37 feet cubed, because it's volume, per second. So anytime we're taking some sort of quantity and then taking its derivative, now we're talking about a change over time. Number 3. This graph is a little bit tricky. The graph above represents the distance traveled by 2 different cars that start at the same position and travel in the same direction. Notice here that the y-axis represents feet, so this is the distance traveled. If you want to think about the y-axis as distance, if you find that helpful, whereas the x-axis would be represented by time in seconds. The y-axis is distance in feet. So the above graph represents the distance traveled by 2 cars that start at the same position and travel in the same direction. All right, so if they're starting at the same position, here's their start. They travel in the same direction, so they're both kind of heading out this distance. The position of car F is given by F of t, and the position of car G is given by G of t. Okay, now G of t is the curve, so make sure you understand that car F is this straight line, and car G is the curve. I know it's sort of because they flip-flop there at the end. Which car is traveling faster at t sub 3? Now, remember that how fast you're traveling has to do with your distance over time. Right now, you're being given information about each car, but we really need to relate this to their slopes. If I'm talking about distance per unit of time, usually when we're, like, for instance, when you're traveling in your car, you measure how quickly you're going in miles per hour. So in this case, we could think about how quickly these cars are traveling in feet per second. So feet per second is the rate of change. And if we are looking for which car is traveling faster, we want to look for which car has a greater rate of change or a greater slope. So we're looking for which car has the steeper slope. In this case, we could definitely say that at t sub 3, the slope of the tangent line at car G looks like this. And the slope of the tangent line for car F, I cannot find my red felt pen. It's driving me bonkers. I've switched to felt and I can't go back now. It's just not happening. I'm not going back ever again. Only flare pens for me. The slope of the tangent line for car F looks like that. So we're talking about the one that has the steeper slope, and we can clearly see that G has a steeper slope. The value of Y is changing more rapidly per unit X than for F. So that's what we're looking at here is the rate of change, the slope. The one with the steeper slope is G. So which car is traveling faster at T3? Well, car G. Because the tangent line is steeper, or because the slope of the tangent line is steeper. And by the way, these examples don't take me very long to go through, but they might take you a little bit of time to understand. So this might be somewhere where you might want to pause this and be like, wait a second, do I really understand what's going on? And think about it, look at it again. Because, I mean, I can only explain it so many different ways. The slope of the tangent line is steeper at G, therefore the rate of change at G is greater. If the rate of change is greater, the speed is greater. When are the cars traveling about the same speed? Well, this is where you want to see where their tangent lines have approximately the same slope. So this is going to be, where do the tangent lines appear to have the same slope? Appear to have the same slope. Where do the tangent lines appear to have the same slope? So this is going to be where, I mean, on the x-axis, what time does this occur? Now, it's hard for you to eyeball, but what you're looking for is if I wanted to, since F is a straight line, if I wanted to create a tangent line on this curve, I want it to have the same slope as F. And where you're going to get that to happen, probably most clearly, is going to be at t sub 2. Because if I wanted to draw the slope of the tangent line at t sub 2, it's going to look like this. And it's going to appear to be parallel to the tangent line at F, for the tangent line of F at t sub 2. So in this case, I could say, when are the cars traveling at the same speed? Well, the tangent lines appear to have the same slope at t sub 2. So we would say at t sub 2. That would be the answer, t sub 2 seconds. All right, so these are kind of tricky. Interpreting the derivative is a little bit harder than actually just computing the derivative. Now, what can be said about the positions of the cars at t sub 3? The positions means where they're located. And we know that at t sub 3, they've traveled the same distance. They intersect here at this value. So we know that the distance traveled by F corresponds here, and the distance traveled by G corresponds to this value. So we would say that they have gone the same distance at t sub 3. So we could say the positions are the same, or they have gone the same distance at t sub 3. They have covered the same distance at t sub 3. Okay. Wonderful. Now we're going to do something like that, but we're going to do it with a little bit of a different type of graph. This time, instead of talking about distance over time, we're going to talk about speed over time, which I think is a little bit, you got to sort of shift the way that you're thinking about this. So here's your graph. The speed is on the y-axis. The speed is, I don't know, it would have to be, we're not even given miles here, but I'm assuming miles per hour. The time is on the x-axis. The time is measured in hours. The given graph represents velocity versus time for two cars. Assume the cars start from the same position and are traveling in the same direction. What can be said about the speed of the cars at t equals 1/3 and t equals 1? Okay. Now, I think it's quicker to answer what's happening at t equals 1. This is sort of like the question that we asked in the previous one about the distance that they had covered at the intersection. At t equals 1, these two graphs intersect. If the two graphs intersect, it means they have the same x value and the same y value at that point. Well, the y value represents speed. So we could say that at t equals 1, the graphs have this, the cars have the same speed, or we could say the speeds are the same. Now, having said that, let's think about what's happening at t equals 1/3, because that's the other question that we need to answer. All right, so at t equals 1/3, and you're going to have to eyeball this. If I say that's about 2/3, this is about 1/3, starting from 0 here at the origin. If I'm talking about the speed of the car, I'm just looking at the value on the y-axis. Well, it is clearly the case that when t equals 1/3, car A is faster. Its speed corresponds to a larger y value, whereas car B, the speed corresponds to a lower y value. So you would say that car A is faster at t equals 1/3. What about the acceleration of the cars at 1/3 and 1? Now, we have not talked very much at all about the rate of change of the velocity. So in the last example, we talked about, okay, well, if you're in your car and you're doing a certain distance over time, we talk about that as speed. But what we're talking about with acceleration is the rate of change of the speed. So the acceleration is the rate of change of the speed. Whoops. So that means basically the slope of the speed. Okay, so the rate of change of the speed is how your speed is changing over time. We're going to talk about this down at the bottom using a second derivative, but it's the rate of change of the rate of change if we're thinking about distance. So if we're talking about the rate of change of your speed, then what we need to do is look at the slopes of the speed. Now at t equals 1/3 and t equals 1, let's see. We're looking here at the slopes of the tangent lines. It's kind of hard to tell at 1/3, but I would say that if you're looking at 1/3, the slope of the tangent line for car A looks like this, whereas the slope of the tangent line for car B kind of looks like that. And it's a little hard to eyeball, but they don't appear to be parallel. I would say that the slope of car A is greater. So I would say that at t equals 1/3, the speed of car A is changing more rapidly. So car A has a greater acceleration. So car A has a greater acceleration because it has a steeper tangent line. Steeper tangent line, greater acceleration in this case, just because we have speed on the y-axis. Now at t equals 1, we'll look at what's happening to the slopes of the tangent lines there. And at t equals 1, we could think about here, the slope of the tangent line to this blue curve is really steep, whereas the slope of the tangent line to the red curve is pretty shallow. So excuse me 1 second. Please turn that down. All right. So at t equals 1, definitely car B in that case has the steeper slope. So we could say at t equals 1, car B has greater acceleration. And for the same reason, it has a steeper slope. Who has traveled farther by 1 hour? So this is a tricky one because it's not the same question that we asked in the previous example where we were like, oh, well, there's an intersection point, therefore they traveled the same distance. That's not what's happening here. Over the course of 1 hour, car A has always had a faster speed because the y coordinate values were always larger. Whereas for car B, the speed was lower and they didn't actually meet to cover that, to be going the same speed until that 1 hour mark. So because of that fact, we would say that car A had a greater speed over the entire interval. It just makes sense logically that car A traveled farther because it was going faster over the course of that hour. So car A, because the speed was greater over the entire 1 hour interval. Okay. All right, so if we have s of t being a position function, then the first derivative is s prime of t, and that gives us v of t, which is the velocity. And usually we measure this in feet per second, but not always. It could be in miles per hour, but for right now, we'll say in feet per second. Okay, that might change depending on what sort of application problem you're working on. But in general, if you've never had physics, you've never seen this before, that's okay. I'm telling you right now, for a position function that tells you your position over time or the distance that you've traveled, its derivative gives you velocity, which means the rate of change of that distance over time. Now, the second derivative is s double prime of t. That's kind of how we use that notation. S double prime of t is v prime of t, and we usually denote this a of t for acceleration. And that is measured in feet per second squared, which might seem odd, but it's feet per second. So the two values in the denominator get multiplied together, thus feet per second squared. So that's kind of how these derivatives work together with the position functions. Let's do another application. A ball is thrown straight up with an initial velocity of 128 feet per second. So its height at t seconds, its s of t is negative 16t squared plus 128t. Find the average velocity over the following intervals. Now, the average velocity, remember, is just the rate of change of the position. Rate of change of the position over time. So for this, if you're finding average velocity, remember that the average velocity going back to that first page was the average rate of change. And the average rate of change is just being represented by the difference between those values, that slope for your secant line. So what we're going to do is we're just going to find those slopes. So we'll say that m is just your position function at t sub 2 minus your position function at t sub 1 divided by t sub 2 minus t sub 1. All right, so if I'm looking for these particular values, I'm going to show you how to find these quickly in your calculator, because you're going to be like, okay, I did this, and then I did it again, and then I did it again, and it was so much work putting it into my calculator, and I don't want you to feel like that. What you can do here is you can absolutely sit there and put all this together into your calculator and evaluate this and that and the other thing, but you might find that that's sort of cumbersome. I'm going to give you the formula for what this would look like, and then I'm going to show you a shorthand to do it into your calculator. So if you're looking for S of T sub 2, well, we'll think about this as if you're looking at an interval, this will be T sub 1, and then the second one will be T sub 2. So you're looking for the slope, which is going to be the position at T sub 2. So negative 16 times 3 squared plus 128 times 3 minus, and then you're going to take off the position function evaluated at T sub 1. So that will be 2 squared plus 128 times 2 divided by, oh, this is going to drive me crazy. Okay, technically, this is not part of your fraction. T sub 2 minus T sub 1, so 3 minus 2. You may absolutely sit there and plug all this in. I'm just very concerned that if you do that, you're going to end up with sign errors. So I'm going to show you how to do this in your calculator so that you can be very quick about it. You could, of course, pick up values from your table. And if you're like, wait a second, doesn't this function look familiar? Didn't I just enter this? Yes, you did. Enter it into your y equals. Whoops. Somehow that went into my y sub 2. That's all right. You know what? Actually, I don't want it in my y sub 2. Negative 16 x squared plus 128x. I'm going to get rid of that. All right, so negative 16x squared plus 128x. This is in my y sub 1. It's important that it's in my y sub 1 because I'm going to pull up that variable. So what I'm going to do is I'm going to use my calculator to evaluate this function instead of having to sit there and evaluate the whole thing myself. So the way that I'm going to do this, you'll be able to see what I'm entering here, is I'm going to go into my variables. Oh, I'm going to go to my home screen first. And I'm going to pick up my variables. I'm going to hit that vars button. I'm going to scroll to the right to yvars, and I'm going to hit enter for function. And I entered my function in y sub 1. What this does is it's going to pull up whatever that function is for y sub 1. And then you can open up a parenthesis and evaluate it wherever you want to evaluate it. So I'm evaluating it first at 3. So I'm going to evaluate it at 3, and then I'm going to subtract off S of T sub 1, which is evaluated at 2. So I'm going to say minus, and then I'm going to pull it up again. Yvars, enter for a function. I'm going to hit 1 again. I'm going to open my parenthesis and evaluate it at 2. Now, this is going to give me the numerator. So it's going to take this function, it's going to evaluate it at 3, and subtract off the function evaluated at 2. What I need to do then is insert, so second delete, insert left parenthesis, because I need my whole numerator in parentheses. And then divide by your denominator, 3 minus 2. Whoops, 3 minus 2. All right, so this will be your function evaluated at 3 minus your function evaluated at 2 divided by 3 minus 2. And you end up with 48. So you could do that the long way and enter that all yourself, or you could just do it in your calculator to save some time. So this is 48. And remember, we're talking about a rate of change of the position over time. So we're going to talk about this as feet per second. 48 feet per second, but you can do the same thing to evaluate all of these. In the next example, if you're going from 2 to 2.5, again, we can do the same thing using our calculators. I'm just going to pull up y sub 1 of 2.5 minus y sub 1 of 2 divided by 2.5 minus 2. And I'm even going to just pull up the same formula on my calculator and just switch out those values. So I'm going to hit second enter, to pull up my last entry. And I don't want 3 and 2. I want 2.5 and 2. So notice we're closing in on that interval. So I'm going to scroll over. I'm going to hit 2, and I'm going to second delete to insert and change that to 2.5. And now it looks exactly like how I want it to look. And as long as I have this function into my y sub 1, it's going to pull up the correct function, and I'm going to get 56 feet per second. So that would be my rate of change on the interval from 2 to 2.5. Now, you can see that as we narrowed the interval, so we went from 2 to 3 and we had 48. But as we got closer and we started to narrow this in on the curve, we started to get a larger value. So I'm assuming that if we get even closer still, we're going to see this slope steepen out even more. So we'll find that now. We'll take y sub 1 of 2.1 minus y sub 1 of 2 divided by 2 sub 1, 2.1. Did I say 2 sub 1? I don't know what I just said. Minus 2. All right, so I'm going to put this in one more time. Second entry, I'm going to swap out the 2.5 with a 2.1. And it's still pulling up that same function I entered in y sub 1. If you didn't enter that correctly, all these values will be wrong. So make sure that that's correct. And you get 62.4 feet per second. 62.4 feet per second. So it did indeed increase. Now, I'm going to give you some leading questions here. So you're going to be like, wait a second, didn't we already talk about this? We did. The question for B is find the instantaneous velocity at t equals 2. The instantaneous velocity at 2, we can find using the derivative. So if you're just like, oh my gosh, now I have to go evaluate this whole thing all over again. No, you don't. It was on page 26. We had the same exact function. It was negative 16t squared plus 128t. We had it with x, but it was the first problem we did today, the first example, negative 16x squared plus 128x. And we found that the derivative f prime of x was negative 32x plus 128. So I'm going to repeat that here so that we can use it to find the instantaneous rate of change at 2. So we know, and I'm going to change the x's to t's, by the way, because we're talking about a function f of t. But I'm going to say that f prime of t is, I already lost it, it was negative 32t plus 128. And this was, remember, from page 26, example 1. Now, once you have your derivative, we can talk about that instantaneous velocity at any given value. When we did this for example 1, we looked at the instantaneous rate of change at 0, and we found the slope to be 128. So let's look at it at 2. F prime of 2 is negative 32 times 2 plus 128. When you add these up, you get to 64 feet per second. Now, the whole idea of finding these average rate of changes before we found the instantaneous rate of change was so that you could sort of see, like, all right, we're getting closer, we're getting closer, we're getting closer. We're decreasing this interval so that we're getting closer and closer and closer to 2. As we did that, we went from 48 feet per second to 56 to 62.4. Then we used the derivative to find the actual slope of the tangent line at 2 to find 64 feet per second. So actually at that point at 2, we have the derivative being 64. And because it's an application problem, we want to make sure that we're putting units in our answers. And in this case, we're talking about distance in feet divided by time in seconds. So 64 feet per second. Part C, find the instantaneous velocity at t equals 5. Is the ball rising or falling at 5 seconds? So we're going to do the same thing. This time we're going to take our function, which is f prime of t. You know, I probably should have called it s and not f. Was anyone else thinking that? Was I the only one? I'm going to change mine to s's just because I want you to make sure that you're saying what you mean to be saying. Oh my goodness. I'm really making good use of this whiteout pen today. It does not matter. I know we called it F on the previous page, but it's technically S here. And I want to make sure that the function is saying what it's supposed to be saying. These were actually S primes. And if you want to even think about it as being velocity, you could say V of t. And then V of 2 was S prime of 2, taking that notation back to what we had discussed on the previous page. So if we're looking for the instantaneous velocity, S prime of t is V of t. And we're looking for that at 5. We'll find V of 5, which is negative 32 times 5 plus 128. And you should end up getting, and by the way, don't put this into your y sub 1 formula because that's not the function that's in there. We have just the S function in there, not the S prime. Negative 32 times 5 plus 128 is negative 32. So this is less than 0. If the velocity is negative, that means that your object is heading downwards. So the velocity is positive when it's heading up or heading away from the original location. When it starts to head back, your velocity becomes negative. Now, I don't want you to think about this the way that you would with time. A lot of times when you have a negative time, you're like, oh, well, we can't have negative time. Therefore, this is not an answer that we're going to use. But your velocity can be negative because a velocity can head back the other direction. And that's all that means. And remember, that makes sense because velocity represents a slope and a slope can be negative. So if the instantaneous velocity is negative, that means that the ball is falling at 5 seconds. All right. And if you want to relate that back to what we did in part B, oh, we didn't actually answer that question. The ball would be rising at 2 seconds because the velocity is positive. Ball is rising. Falling means it's negative. Okay. When does the ball hit the ground? We kind of did something like this when we did that basketball example at the way beginning of chapter 2. But the ball is going to hit the ground whenever its position is 0. So 0 feet position, that means the ball is hitting the ground when the position S of t equals 0. And if you think about this as the position being along the y-axis over time, I mean, the ball is going to go up at some point, and then it's going to head back down again. We already looked at the function, so I have a good idea of what it's doing. Knowing what that function did, I find it funny that it's being used in context of a ball in the air, but I mean, maybe it's a baseball that can go really high. It's going to go up, and it's going to come back down again. So it must be that at some point, it hits this highest point, and then it heads back down again. Now, the position S of t is 0 whenever y is 0. So that's going to fall along this line. So what we need to do is just figure out the values for which S of t equals 0. I'm going to pull that function back up again. Remember that you were told at the beginning that S of t was negative 16t squared plus 128t. If I want to solve that, I'm going to set this equal to 0. You can factor 128 divided by 16 is 8. So I can take out a negative 8t as the GCF, and that leaves me with 2t, and then minus 16 equals 0. That means either t equals 0 or t equals, when you solve this equation, you could say 2t equals 16 or t equals 8. So t equals 0 was the first place where the position was 0 right down here. T equals 8 is the second place where your position is equal to 0. So now you can see how it makes sense where somewhere in the middle here, you hit this highest point. That highest point is going to correspond to 4. And a lot of what we're going to be doing in the next chapter and the chapter after that, specifically the chapter after that, is being able to determine where this highest point occurs. And that has to do with where your slope is equal to 0. And we will talk about that later on down the road. But just wanted you to start thinking about it right now. But you can sort of see how if the velocity is negative at t equals 5, well, it makes sense because it must be that somewhere between 4 and 8, like anywhere between 4 and 8, you're going to see that the slopes of the tangent lines will be negative. Between 0 and 4, the slopes of the tangent lines will be positive. So the velocity is positive until you get to 4, and then it starts to become negative. T equals 8 seconds is where the ball hits the ground and it stops its journey. How fast is it going when it hits the ground? Well, how fast you're going is the rate of change. That's your velocity. So that means find the velocity at 8 seconds. That means you're finding v of 8. Well, you have a velocity function already. That was from your derivative. Whoop, it's up there. V of 8 is negative 32 times t, which in our case is 8, plus 128. So negative 32 times 8 plus 128 is negative 128 feet per second. And remember, we said that's okay. It can have a negative velocity, and it has to have a negative velocity in this point because it's heading down. And it makes sense that this velocity would be increasing. It goes fast, fast, fast. It slows down. It gets to its highest point, and then it starts to head down again slowly, and then it's going to pick up speed on its way down. So negative 128 feet per second is how fast it's going at the point in time that it hits the ground. And then, of course, it hits the ground, and who knows what it does after that, but we don't care. That's the speed at which it hits the ground. All right, the last thing we're going to do in this section is talk about differentiability. It is important. It's not something we're going to deal with every single day, but in chapter 4, it's going to be a little bit more important to some of the things that we're going to be doing there. So a function is differentiable. A function is differentiable at x equals c if f prime of c exists. So you're like, okay, well, that seems like it makes sense. Yes, but we need to talk about situations where that might not be the case. Now, it's a little bit hard to tell just because of the overlap here, but this green curve is actually like sort of like two curves together. It's not a smooth curve. It has this sharp point to it. So it hits this point and then it goes and it kind of cups downward like that. What ends up happening is it's because you have this tangent line that would be approaching the curve at that point. But then when you switch the curve, it's almost kind of like it's a piecewise function. This tangent line, this red one, actually is controlling the slope on the right leg of this curve. So what ends up happening is you end up getting a sharp point here. If you could continue these tangent lines on their path, you would see that you have a sharp point on the graph. This is problematic for your derivative. It cannot be the case that your function is differentiable at this point because the derivative would not exist. F of x is not differentiable at a. So sharp points are one of the big things that you need to look out for when we're talking about differentiability, just because you end up having two different tangent lines. So it cannot be the case that the limit would exist because they're not approaching the same value and the derivative is controlled by a limit. Let's see, as far as continuity is concerned, if a function is differentiable at x equals c, then it's continuous at x equals c. Okay, so if a function is differentiable, then it is continuous at that point. So differentiability implies differentiability. Did I totally spell that wrong? Differentiability implies continuity. So differentiability is a very strong condition. Now, this logically also means that if it's not continuous, that means it's not differentiable. Okay, so if a function's not continuous, it can't possibly be differentiable at that point of discontinuity. It cannot be. How would you be able to find the slope of the tangent line if the graph has no tangent line? And a very important point, and we must be cautious because continuity does not imply differentiability, as you can see from this graph above. Continuity does not imply differentiability. You can have a function that's continuous at every point along its domain, but that does not mean it's differentiable at every point. If we picked a different point that was not at A, I mean, you could pick a point over here and your function would be differentiable, or over here. But this function's continuous on its entire domain. You can graph it without lifting your pen, but it is not differentiable at that sharp point. Therefore, continuity does not imply differentiability. So you can't just say, oh, the function's continuous, therefore it's differentiable everywhere. Not the case. So a couple things you need to look for would be these cusps or corners, like sharp points on your graph. So if you have a sharp point on the graph, that means that you are not going to be differentiable at that value, just specifically at that value. If your function is not continuous, then it's not differentiable. I mean, you can see, how could you possibly have a slope of the tangent line? You don't even have a tangent line. So this is a big no-no. And then if you end up with a graph that has a vertical tangent line, oh, I always forget what graph has a vertical tangent line. Why do I want to say it's like, I don't know, like 1 over x. There are a bunch of them. I'm looking for it real quick for you. 1 over like x to the 5th, maybe. It has one that's really clear. No. X to the, I don't know, I gotta think about this. There's one example that I always use for this, and it's eluding me right now. It's like x to the, how to find it? 1/5? Okay. So I entered x to the 1/5 power. I don't know, this is just my standard, like this is not differentiable at 0 situation. You can zoom in. I'm gonna hit zoom 2 and then enter. You can kind of see that there's this gap in the graph. And the reason is your calculator can only graph functions. And at this point, the graph appears to be vertical. So your calculator actually can't graph a point there. So it's showing a gap. So this would be a situation where it has a vertical tangent line. It just has this point at 0, 0, but the tangent line would be vertical at the point. Therefore, we would say that this function is not differentiable at 0. If you actually went to your table, you would get a value at 0, and the function's continuous at x equals 0, but it's not differentiable. If you were to actually take x to the 1/5 and try to find its derivative, and you would go through and find the limit as as h approaches 0 of f of x plus h minus f of x divided by h. And then you evaluated the derivative at 0, you would find that the derivative does not exist. You can do that on your own. And if the derivative does not exist at 0, then the function is not differentiable at 0. So the way that would present itself on a graph is with this vertical tangent line. So just some things to look out for: sharp points, vertical tangent lines, discontinuities. These are all places where your graph is not going to be differentiable. So you'll see some examples of those on your homework, and you'll go through and figure out which one's differentiable at this point and which one's not, so on and so forth. I know that was like a totally loaded topic on differentiability. Please let me know if you have questions as you work your way through this homework, because I know there's a lot. And then the next chapter will sort of shift gears a little bit and talk about rules for differentiation so that we don't have to use that difference quotient. I don't know why it always eludes me. Okay, so we'll do that. And we'll be focusing a lot on derivative rules and some more applications in chapter 3. But this is it for chapter 2. These sections 2.1 through 2.6 will be on your first test. Okay, so let me know if you have questions. Have a wonderful rest of your day. I'm going to go attend to my 4-year-old. Adios.